So we've been focusing on the definition of Avogadro's number as the number of hydrogen atoms in 1 gram. What would a mole of some other elements look like? Chemists were very clever in coming up with all of these definitions so that the decimal values on the periodic table have a dual meaning. The first meaning is it's the relative mass of each element. Now that's compared to 1/12 the mass of a carbon-12 atom. Because a carbon-12 atom has 6 protons and 6 neutrons, this new standard for relative mass has roughly the mass of a proton or neutron, sometimes called a nucleon. This amount of mass has been given the name an atomic mass unit. That's sometimes abbreviated AMU or simply U. This is very close to the mass of a hydrogen atom because the most common hydrogen atom consists of just a proton and an electron. The more useful meaning of the decimal numbers on the periodic table is that they represent the molar mass of each element. That's the mass of 1 mole of each element's atoms, measured in grams. For hydrogen, this is 1.01 grams. 1.01 grams of hydrogen has Avogadro's number of atoms in it. That's 602 sextillion hydrogen atoms. How much would this be? It's hard to tell because hydrogen is a gas, but it would be about 11 liters of gas. You can see here a liter cube. Imagine 11 of those. That would contain about 1 mole of hydrogen atoms. What about carbon? If we look up carbon on the periodic table, we see that its molar mass is 12.01 grams. So I'd like to show you exactly what 12.01 grams of carbon looks like. I'm going to zero my scale, put a weighing dish on, and zero it with the weighing dish. And I'm going to start adding pencil leads. Now really these are graphite sticks. They're not made of lead anymore. And they're pretty much pure carbon. If I want to measure out a mole of carbon, I need to measure out 12.01 grams. I'm getting pretty close here. This balance only goes to 1 decimal place, so 12.0 grams will do. So assuming these graphite sticks are pure carbon, I've just weighed out 1 mole of carbon atoms. If you wanted to know, that's about 190 of these graphite sticks. It's 0.9 lead if you're curious. Next, let us consider iron. Iron's molar mass is 55.85 grams per mole. Again, that means 602 sextillion iron atoms have a mass of 55.85 grams. For iron, I'm going to use these iron nails. If I want to count out a mole of iron atoms, I need to measure out 55.85 grams. Again, I zero my scale with a weighing dish and start adding nails. My goal is 55.85 grams. That's pretty close. I think that's good enough. Again, I've counted out 602 sextillion iron atoms because I've measured out 55.85 grams. That's 1 mole of iron atoms. Or roughly 8 large nails. What if I wanted to measure out a mole of water? Well, think about what water is made of. Water is made up of H2O molecules. So each H2O molecule has 2 hydrogen atoms and 1 oxygen atom. Let's go to the periodic table. We know that hydrogen has a molar mass of 1.01. Oxygen has a molar mass of 16.00. So if you think about a mole of water molecules, you're going to have a mole of oxygen atoms. You're also going to have 2 moles of hydrogen atoms. So that's not going to be 1.01 grams. That's going to be 2.02 grams. So if I want to measure out 1 mole of water molecules, I need to measure out 18.02 grams. 18.02 grams of water will contain 602 sextillion water molecules, 1 mole. I'm going to measure it out the same way. Zero my balance and start adding water. My target is 18.02 grams, or around 18.0 on this particular balance. Let's see how close I can get. Looks like I went a little bit too far, so I'll remove a little bit with a pipette. There, I've got it. Now, you might also know about water is that it has a density of 1 gram per milliliter. So if I poured this volume of water into a graduated cylinder, it should equal right around 18.0 milliliters of water. Let's see what that looks like. Hopefully you can see here that it's right at 18 milliliters. And last, let's consider sodium chloride, table salt, NaCl. If I wanted to weigh out 1 mole, 602 sextillion units of NaCl, I need to go to the periodic table and see that the molar mass of sodium is 22.99 grams per mole. The molar mass of chlorine is 35.45 grams per mole. Since a mole of sodium chloride units would have an entire mole of sodium and an entire mole of chlorine, I have to add those two numbers up to get the molar mass for the compound. That's 58.44 grams per mole. If I measure out 58.44 grams of sodium chloride, I will have 602 sextillion NaCl units. So let's measure it out one last time. I zero the balance with a weighing dish and start pouring in sodium chloride salt, the same kind you would get at the store. I made sure it's not the iodized kind because I don't want iodine in there. I just want sodium chloride. My target is 58.4 grams on this balance. We'll see how close I can get. It's a bit too much, so I'll remove a little bit, just a pinch. That'll do nicely. 58.4 grams, 1 mole of sodium chloride. In other words, 602 sextillion NaCl units. And that quantity we call 1 mole. So we see 1 mole of carbon atoms, 1 mole of iron atoms, 1 mole of water molecules, and 1 mole of sodium chloride. It's not intimidating at all. 1 mole is an easily measurable quantity in the lab. We just go to the periodic table to see what its mass would be for that particular material. The entire mole concept is about counting chemical quantities. Typically in the lab, you can measure the mass of a sample in grams very easily. From that sample, using the molar mass, we can convert quantity in moles. Again, we get the molar mass straight from the periodic table. We set up a conversion factor of how many grams are in 1 mole for that substance. Most of the time, that's where you'll stay in chemistry, converting between grams and moles back to grams. Occasionally, a problem will ask you to calculate how many atoms or molecules or formula units are in a sample. We typically don't need to do that in the lab, but we can do it if we'd like. We use Avogadro's number. Avogadro's number just tells us how many of those things are in 1 mole. Just like a dozen always has 12, a mole always contains 602.2 sextillion things, or in scientific notation, 6.022 times 10 to the 23rd power. What you're actually counting depends on the sample. If you have a pure unbonded element, you're counting atoms. If you have a covalent compound, something covalently joined with shared electrons, you're counting molecules. And for ionic compounds, which are not made of molecules, you're counting formula units. It's a subtle distinction, but it is important. You can see in this picture of water molecules, you have distinct particles, molecules. If you have something like table salt, sodium chloride, there are no individual molecules. If you look closely, you can pick out formula units. In this case, that formula unit would contain one sodium ion and one chloride ion. But it is not correct to call that unit a molecule.